Okay, this is the final thing that I wanted to highlight. It shows you the actual mean difference. Okay, so that was the t-test. Now let's move to the sample proportion test. What happens when you want to compare not the mean of two different samples, but a proportion of two different samples? That's what actually happens when your dependent variable is not numeric, but is categorical. With nominal or ordinal variables, you cannot compute the mean of those variables. You need to compute proportions. And then, for instance, in this example, you want to compare if the difference between men and women in terms of the support to abortion is significant or not. Again, you have a difference of 4 points, and you want to see if that's relevant or statistically significant or not. Okay? Remember some notation related with proportions. Remember that we use P to talk about the proportion of cases falling into one value of the variable of interest. That is actually that value that we want to explain. For instance, in this case, in terms of the dependent variable, we want to explain support of abortion, which is yes. And Q is the proportion of cases falling into all other categories. Okay, in this case, no. And our hypothesis is that women are more likely to support abortion than men. Okay, that is what we saw here. The null hypothesis here is that there's no actual difference in the population in these proportions. Okay, so something that is important is that all the principles and the way that we estimate the sample proportion is basically, or the same logic of the sample mean comparison is the same to the sample proportion comparison. Okay, the formula is a little bit different, as you can see here. Okay, but the rest is the same. In what way? In the way that we, for instance, we estimate the formula for the standard error of the proportion difference is what is different, but the test is basically a t-test. Usually with sample proportions, we use the c-test. So we assume that the distribution is normally distributed, and it's the same kind of formula. So we subtract the difference, the expected difference in the null hypothesis, which is 0, to the difference expected by our hypothesis, and we divide that by the standard error of the proportion difference. Okay? The interpretation again is the same. You use the c-values and the p-values to examine the extent to which you can reject the null hypothesis, or you can use the eyeball test for statistical significance. In this case, for example, the c-value was 1.2. So let's see what is 1.2. 1.2 is actually here, and there is a chance, it is slow to some extent, but there is a chance that the probability, the rest of the probability under the curve, which is 11% of the distribution, there is a chance of 11 out of 100 times that the null hypothesis is true. So I want to highlight here that this is still a high, like a very, or better. I want to highlight here that this is still a very small or very low probability. If you can see here, it's just 11%. So it's not very high. In other words, what I'm trying to highlight here is that we use a very high threshold to reject the null hypothesis, right? So again, what I'm trying to say here is that we try to be rigorous with our scientific results, and that's something that is important to keep in mind. Okay. Okay, so how do we estimate the proportion test in R? So again, we're gonna use the same data set. We're gonna create a variable called approval. This is the approval of President Trump in 2018. And we collapse an ordinal variable and we create this nominal variable, disapprove or approve. Okay. Now, there's something important that we need to some extent estimate the frequency of women and men in the sample that we have. And in order to do that, use the tidyverse, use group by female and count. And you're gonna see in the console, notice that I didn't create an object for this. So you're gonna see in the console these frequencies. And later you need to see, or you need to know, the frequencies of ones or the frequencies of support to President Trump, in this case, distributed by gender. Okay, so you use this group by female approval and you're going to have the count. Okay, you need to write down those numbers because you're going to plug those numbers in the formula. Okay, a little bit of background. So imagine that we want to examine the relationship between gender and the approval of President Trump, and we claim that men are more likely to approve the government of President Trump than women. We estimate a proportion difference of 12 percentile points of difference, which is actually very high. And we want to know if that difference is statistically significant. We suspect that it is, because it's actually high. It's 12 points, it's a lot. Okay, we use the proportion test function, but first, please see this function. See the structure of the function. You don't have variables here. You don't have data sets here. You need to plug in numbers, okay? So you're gonna have this x equals c, and you're gonna have here the first value is gonna be it's gonna be actually p, or which is the support to Trump in the male population, and you're gonna have the support of Trump in women population, and you're gonna have this n. There's a comma here, but you can see here. N, again, you're gonna have the first value is gonna be the sample of men in the CCS, and later you're gonna have the sample of women. The size of the sample is what I mean. Okay. And you're gonna use again this function of greater because we are saying that men, or the proportion of support of Trump in men is higher than the support of Trump in women. Okay. And remember that these values, we estimated them with the formula that I wrote of the tidyverse. Okay. Again, this function proportion test is part of the package of R, so you don't need to download it. And the results are the following. You're going to have a very small p-value again, so you can confidently reject the null hypothesis. Okay. Another thing that is interesting is that the function gives you the confidence intervals, which in this case, see that both the lower confidence and the upper confidence boundary are higher than 0, so you are fine. You can again reject the null hypothesis, and you see the actual proportion difference, 12 percentile points, which is very high. Okay, that's the proportion test, and you use it with categorical variables. Okay, there is another test that you can use with categorical variables. This is called the key test. As you can see, one of the limitations of the t-test or the proportion test is that you are only comparing two categories of the dependent variable, right? But sometimes you have ordinal variables or nominal variables with several categories, not only two categories, but I don't know, 5, 6 categories. So what do you do in those cases? How do you know that the independent variable is actually related with the dependent variable? That's why the chi-square test is useful. Look at this example. For instance, we want to see the relationship between gender and support to homelessness, or not support, like a support to different kind of policies related with homelessness. You can see here, this is an ordinal variable that goes from carrots to sticks, like a more strict kind of measures to control homelessness. Okay, so the key test helps you to try to see the independence between these two variables, and for that reason it's very powerful when you have categorical, like a cross tabulations and this kind of categorical variables. Okay, the logic of the key test is to some extent different to the logic of the t-test and the proportion test. In the t-test, you want to see the extent to which the data is dispersed, okay? And the null hypothesis is going to be kind of idiosyncratic to some extent, or very interesting. And this is the null hypothesis. So you are saying that if the null hypothesis is correct, the total distribution of this column of the total distribution of the data should be reflected in the different categories of our independent variable. Okay, so instead of something like a 46.2, for instance, in the cell of carrots and women, we should see something like a 40%. Instead of 46% falling in this category, you should expect something like a 40% falling in that category. And the null hypothesis claims that each or a departure from that distribution is just random. Okay. Here I want to highlight something that is very important, and is why it is important to set the table in this way, in a way that is like a determined to some extent by the distribution of the independent variable. In this case, the total in this column. So again, so to some extent, some of you asked a question of why we should have the tables as Pollock suggested to have the tables, and it's because we can sum here. The sum here is the column and not the rows, right? If it were the rows, if the distribution or the frequency were based on the distribution of the dependent variable, we should have here 100%. And we were not able to conduct this kind of analysis, okay? So for that reason, it's important to maintain this kind of structure that is very standard in political science, okay? So again, notice that here, the way that we set this table is that we're going to have the total here is going to be the values, the sum of the column, okay? And this total actually is very interesting because it's not the sum of the rows, okay? So I'm not going to have here, for instance, the 100% of people who prefer carrots. I'm not going to have that. I'm going to have here from this column the percentage of people who prefer carrots, which is the 40% prefer carrots. Do you see it? So that's important. It's important to understand the difference, okay? So it's going to be, our actual total is going to be the columns, okay? Always going to sum 100%. And Pollock emphasized this a lot. And I want you to keep this structure. Don't change this structure, okay? Okay. So to estimate the t-test, you need to understand the difference between the observed frequency and the expected frequency, but it's related with what I already explained to some extent. So the observed frequency is simply, in this case, 245 in the cell carrots women, and the expected frequency, is what might be this frequency if in this cell were not 46.2 but 40.4 as the null hypothesis claims. Look at here. That value would be something like a 214 women supporting carrots instead of 245. So the formula is basically the sum of the differences of those two kind of frequencies, and those frequencies are squared and are divided by the number of expected frequencies. Something that is important to highlight here is that if the frequency, the observed frequency, is equal to the expected frequency, this value would be 0, right? And everything here would be 0. So the t-test would be 0, okay? Now, think about it a little bit. If the observed frequencies were the same as the expected frequencies, which is what we need to have in order to have this, the numerator as 0, if that happened, That's actually what the null hypothesis is claiming. It's claiming that there is no actual difference between the expected frequency and the observed frequency in the population. Okay? For that reason, that's zero, and the t-test would be zero, and we would not be able to reject the null hypothesis. Okay, so similar to the c values and the p values, we want very high levels of the chi-square in order to be able to reject the null hypothesis here. Okay, or in other words, what we want to have is a very high observed frequency, or could be very low, but different to the expected frequency in order to have to be able to reject the null hypothesis here. Okay. So to interpret the t-test, it is the t-test has its own distribution, and similar to the student t-distribution, this distribution is affected by the degrees of freedom. So notice the difference between 2 degrees of freedom and the distribution, and the difference with 2 degrees of freedom and 6 degrees of freedom. In the figure of the top, you can see that this is the chi-square value. If in order to have the chi-square value to be whatever, so let me say in this way. So if you have something higher than 5, for instance, in the chi-square value, the probability is very, very low. But if you have something between, I don't know, probably 2 or 3 and 0, that value, also the probability is very, very high. Okay? And that's going to change with 4 degrees of freedom and 6 degrees of freedom. The density is always going to be the expected likelihood of occurrence of that event. In this case in this type of figures, of distributions. Okay? So again, just to summarize, the chi-square has its own distribution and is also affected by the degrees of freedom. Okay? How do you get the number of degrees of freedom with a chi-square test? You basically need to use this formula. It's the number of rows minus 1 times the number of columns minus 1. In our case, that value is 2. So the degrees of freedom is 2. So we are in this figure. Okay? And we need to have a chi-square value higher than 5.9, which is probably here, to reject the null hypothesis. If we are in this range of values of the chi-square, we are not confident to reject the null hypothesis. Okay? We actually got a chi-square value of 15.2, which is here. So the null hypothesis, or the probability of the null hypothesis, is very small. And we're going to have the 3 stars of the p-value. Okay? Okay. So what are the limitations of the chi-square? And notice that this is the first time that I talk about limitations of the test. Or no, actually no. I said that the t-test, the proportion test, the limitation is that you are only comparing 2 categories of the variables. But okay, one of the limitations is that the chi-square is affected, or is not, it doesn't work very well when you have low variation in the dependent variable, with most of the values in the dependent variable, or better, when one of the categories of the dependent variable is most populated, or is more populated, I'm sorry, than the other categories. Okay, so there's no variation. Okay? In such a case, the best way to solve this problem is to collapse the categories. And instead of having, I don't know, 7 categories in a nominal or an ordinal variables, you can have just 3 or 2. And that's always going to be better for the analysis. And remember, one of the labs that we had, I think, was religion. And you had like 7 categories of religion, and you wanted to see if Christians were more likely to support abortion than the other religions. And it was very hard to interpret it sometimes, because one of these cases, Buddhist, for instance, which has a very low frequency in the state of preference that you selected, was probably an outlier or something like that. So that's one of the problems. So in order to solve that kind of problems, the best way is to have fewer categories. For instance, in that case of religion, just have Christians, non-Christians, and non-believers. I don't know. Okay? And the other limitation of the chi-square is that it's very sensitive to sample size. And when the sample size is very small, or actually better, when the sample size is very large, as in the case of the CCS, you almost always going to have statistically significant results. Okay? Okay, how do we conduct this key test in R? So we're gonna keep using the CCS dataset, and we're gonna prepare an ordinal version of presidential approval. In this ordinal version, the only thing that we're gonna do is to exclude the category 5 because it's not sure. So I don't want to have that category because it's not meaningful. And imagine that we want to re-examine the relationship between gender and approval of President Trump, but we're going to use the whole or all the categories of this variable instead of just one or two. Okay? There's nothing new in this formula. Basically, you use the key test. This is the function, and you write here the variables that you want to use. Something that is important is that you use here, let me see here, so I guess in this case is gender. So the first one is going to be your independent variable, and the second is going to be your dependent variable. But there's a chance that I made a mistake here, but that maybe the first one is the dependent variable and the second is the independent variable. But I'm gonna tell you what is the correct here. But for now, just know that this is the structure of the function, okay? This is not very important right now, but we need to double check that if you want to use it in your applied project. Okay, and what is the result of this? The result is basically, as I said, is expressing x squared values. And look at here, the x squared value is very, very large, it's 1000. And remember that with 2 degrees of freedom, if you have something higher than 5, it was more than enough to reject the null hypothesis. You have here 1000, so you can confidently reject the null hypothesis. And your p-value again is very, very small. Is again, you have 16 zeros after the decimal point, so you reject null hypothesis. Okay, so it's time for a break. We have talked a lot. We have talked about the logic of bivariate differential analysis, and we introduced and we presented in a more rigorous way this idea of the null hypothesis, and this idea that we want, when we are saying that something is statistically significant, is because we are kind of confident that the result is not created by chance. It's not created by the process of drawing the sample. It's actually a significant or kind of robust result. So we are confident to reject the null hypothesis. Thus, all those things imply when we are saying that the results are statistically significant. In order to know that and to don't make an inferential mistake or type 1 error or type 2 error, we use a very high threshold to reject the null hypothesis. Okay? We explain how to use the test statistics or the t-test. We explain what is the t-test. We explain what is the proportion test, and we explain what is the chi-square test. Okay? Don't worry about mathematics. I'm not going to ask you about that. Worry or try to be knowledgeable about what are the assumptions related with this test and how to interpret this test. Okay, that's the most important thing right now. Okay, that's the break.